Good morning, everyone. So, today we are going to start a new chapter, Laplace transform. In this chapter, we will see very interesting technique to solve mainly first order and second order differential equations. In today's class, in today's section, we will talk about the existence of Laplace transform. So, let f of x be any function defined on closed interval a b, then Laplace of f of x, which is denoted as capital F of p, is equal to 0 to infinite integration from 0 to infinite e raised to the power minus px f of x dx. So here f of p is said to be Laplace transform of function f of x, and f of x is the inverse Laplace transform of f of p. Yes, there are some standard result. First we are going to quickly cover them, which we need to remember. So the first one is the Laplace of 1. So it is integration of e raised to power minus px dx. One quick observation is that this integration would be equal to 1 by p only when p is greater than 0. Then only when you put the limit infinite, that becomes 0. Otherwise it would be infinite, but you can say that the integral may not be convergent. Similarly, if you compute Laplace of e raised to the power ax, then it becomes e raised to the power a minus p. But to integrate it, you would consider it as e raised to the power minus and p minus ax. And in that case, again it comes out to be 1 by p minus a, provided p is greater than a. Now compute the Laplace of x raised to the power n. Please do try it by yourself. So when you try to compute it, you will realize that it comes out to be e raised to power minus px, x raised to the power n. So if I consider e raised to power minus px as first function and x raised to the power n as second function, then this is what I got. So if you see the first term, x raised to the power n e raised to power minus px by p, when x is 0, this term is 0. When x is infinite, then also it is 0. Yes, we discussed it earlier also, we will discuss it now also. So the second term is of the form, or it is of the form x raised to the power n by e raised to the power px when limit x tends to infinite. So if you apply the L'Hopital rule, you differentiate it once, that becomes n. So it becomes limit x tends to infinity n x raised to the power n minus 1 and p e raised to power px. You keep applying the L'Hopital rule, so numerator will become p n factorial p raised to the power n and e raised to the power px, which is equal to 0. Now if you see the second term and if you integrate it again, then you will get n minus 1, and here you will get x raised to the power n minus 2 and the denominator p square. If you keep doing it, so something like this, n by p and Laplace of x raised to the power n minus 1. Next is n by p multiplied by n minus 1 by p and Laplace of x raised to the power n minus 2. And if you keep doing it, then in the end you will have n factorial by p raised to the power n and Laplace of 1. We have just seen that Laplace of 1 is 1 by p. That's why Laplace of x raised to the power n, where we are considering n to be a natural number, is n factorial by p raised to the power n plus 1. Okay. Now compute Laplace of sine ax. Again, try it by yourself. So if you go by the definition, it may take a lot of time. But if you observe that we have computed the Laplace of exponential function, and it is easy to write down sine ax in the form of exponential function, and then if you use the Laplace of exponential function, then it's very quick. So it is Laplace of e raised to power iax minus e raised to power minus iax by 2i, and we have just seen Laplace of e raised to power ax is 1 by p minus a. Using this, it comes out to be a by p square plus a square. Please do remember it. And in the same way, Laplace of cos ax comes out to be p by p square plus a square. And similarly, you can compute the Laplace of sine hyperbolic ax and cos hyperbolic ax. Okay, so these are some standard result. It's good to remember at least the first five, which we are going to use quite often in the next section. So before moving to the sufficient condition for the existence of Laplace transform, we need to introduce a new term, which is exponential order. So we say that any function f of x is of exponential order if it can be bounded by exponential function, which means f of x is less than equal to m e raised to the power cx, where m and c are the constants. Okay, it would be clear once we discuss few examples. So what do you think? Is a bounded function is of exponential order? You already know the function is bounded. So for example, you already know the function f of x is less than equal to m. It is bounded. So I can write down it as mod f of x is less than equal to m e raised to the power 0x. And it means that there exist m and c for which f of x is less than m e raised to the power cx, and therefore bounded function is of exponential order. What about x raised to the power n and e raised to the power x square? Now again, quick observation says that if you consider e raised to the power x square, it is not possible to find any exponential function such that e raised to power x square is always less than equal to e raised to the power ax. Yes, because x square is increasing faster than e raised to the power ax. But in case of polynomial, you can observe that yes, it happens. Yes, so if I talk about first x raised to the power n, then I know that e raised to the power ax can be written as x a raised to the power n by n factorial, which is for sure greater than x raised to the power n a raised to the power n by n factorial. It means I keep x raised to the power n on this side and take the other terms on the other side, which clearly shows that x raised to the power n is of exponential order. But e raised to the power x square is not. So x raised to the power n is of exponential order, but e raised to the power x square is not. Yes, again we are not going into the detail that how do we prove it. We just want to see what does it mean, because it is required for the sufficient condition for the existence of a Laplace transform. So sufficient condition says that if f of x is a piecewise continuous function and is of exponential order, then f of p always exists. Piecewise continuous means something like this. So it is continuous over the interval, but there is a jump discontinuity at the end point. Jump discontinuity means these limit exist, but left hand limit is not equal to right hand limit. This is jump discontinuity. So we are not going into the detail of the proof, but we can discuss some remark from here. The first remark says that the above condition is not necessarily. So it's not necessary, which means that there may exist or if a function is not piecewise, or if a function is not of exponential order, in that case we cannot say anything. Laplace transform may exist or may not exist. For example, if I consider function 1 by root x, then clearly it is not piecewise continuous. Think why it is not? Because it has x is equal to 0 is a point of discontinuity. It is not continuous at x is equal to 0. Yes. Now we will see that does Laplace transform exist for 1 by root x. So use the definition, see what will happen. So this is Laplace of 1 by root x. Now to conclude, I need to proceed further. To proceed further, I took px is equal to t. So take px is equal to t and see what will happen. If px is equal to t, then p dx is equal to dt. Then substitute the values, limit would not change. And this is how it looks like. E raised to power minus t, then root p by root t, which is 1 by root x. And dx is 1 by p dt. If you simplify it, you reach here. Mainly the integral is e raised to power minus t raised to power minus half dt. And now again you are stuck. What's its value? Do you know its value? So if you see this one and recall the gamma function, yes, so what is gamma n? So integration 0 to infinity e raised to the power minus x, x raised to the power n minus 1. So this is gamma half, and gamma half is root pi. So it becomes root pi by, so this is root p and gamma half, which becomes, we discussed in the last class, that it is root pi by root p. Yes, provided p is greater than 0. It means the Laplace of 1 by root x exists, and therefore the given condition is not necessary. The next remark says that limit p tends to infinity, f of p is equal to 0. It means that if there is a function f of x for which Laplace transform exists, so limit p tends to infinity of that Laplace transform is always 0. If you see Laplace of 1, Laplace of e raised to power ax, Laplace of sine ax, when you put p tends to infinity, all of them are equal to 0. Again, I am not discussing its proof, it is given in the book, but it gives a very interesting conclusion which says that if limit is not equal to 0, it means there does not exist a function f of x for which f of p is a Laplace transform, or for f of p there does not exist a function f of x such that f of p is L of f of x. For example, if you consider f of p to be p sine p e raised to the power p and so on, for all of them the limit p tends to infinity, f of p is not equal to 0, it means they are not the Laplace transform of any function. So if you have to check if the given function of p is a Laplace transform of any function of x, then you simply need to check that the limit f of p tends to infinity is 0 or not 0. Okay, now let's quickly do two questions, and in the next class we will see how to solve the differential equation using Laplace transform. So first try Laplace of e raised to power x square does not exist. Now Laplace of e raised to power x square, e raised to power x square is not of exponential order, but from that we cannot conclude anything. So we have to go by the definition. If you go by the definition, this is what it suggests. Now I cannot say that this interval 0 to infinite e raised to power x square minus px dx is convergent or not. So to proceed further, think over it how you can proceed further. You introduce e raised to power minus p square by 4. So multiply and divide. and that gives you in the bracket e raised to power x minus p by 2 whole square dx. Now take x minus p by 2 as some other variable y or t, whichever you want. If you take it, then limit would change, but you will get e raised to power y square dy. Now e raised to power y square is an increasing function, so from there you can directly say that this limit b tends to infinity does not exist, and it means Laplace of e raised to the power x square does not exist. Similarly, try one more question, Laplace of x inverse. By definition, you will reach here. Now think what you do next. So you take px is equal to t, other variable, and see what happens. When you take px is equal to t, then it get transformed into 0 to infinite e raised to power minus t by 1 by t dt. Now what's next? So again, if you recall gamma function, this is gamma 0, and we know that gamma function is not defined for 0 and negative integers. Therefore, the Laplace of x inverse does not exist. So that's all from today's class. Thank you.